Hello, I'm Carlos Rosa Suarez and this is the CRS channel. I'm going to continue with the physics problems in kinematics, and we're going to finish problem 10. Okay, so here we are again with the spreadsheet, and here we have the blue line, which corresponds to the velocity for the free fall. We have that straight line. We have the curve here for the free fall, the line for the free fall, which is with the blue line, and it corresponds to parabola. For the y versus t graphs, and this is the horizontal line for the acceleration for the free fall. It corresponds to the blue line. For the case of air resistance with k equaling 0.011 over second, then we have these columns for the data. We can see here that we have used the equations for the velocity. In this case, this equation here, v of t equals minus g over k times 1 minus exponential of minus kt. So this is 1 minus a68 is g, and b68 is k. A68 and B68 is k, with k equaling 0.011 over second. One minus exponential of minus kt. Remember the t here is I69, which is this cell here. Here we have the expression for the position, which corresponds to this formula here, y0 minus g over k times t plus g over k squared times 1 minus exponential of minus kt. And here we have it. D68 is this one, which is y0 minus g over k times t minus g over k squared times exponential of minus 1 minus kt, and that minus 1. And the expression for the acceleration, which is simply a equals minus g minus kv. Since v has already been calculated, you can notice that the values of v are in column J. So this is J69, which is the value used here. So we have minus k minus g minus kv. So we have these values. Now you can see that the values of the acceleration down to the time which the object or the body approximately reaches the ground which is the acceleration is minus 8.466 meters per second squared approximately, is not very far off from minus 9.8. That means that if you look at the values for velocity and position in comparison to those for the free fall, you will notice that the values are not very different from those of the free fall. For example, here we have minus 119.56, F minus 112.555, and the position here is 299.46 meters, and here it is 270.684. And you can notice that the fall time is very close to that for the free fall. If you look at the graph, you notice that the acceleration, of course, is not so far off from although the line, you can observe a line, this is the red line, corresponds to k equals 0.011 over second, has a slope with respect to the corresponding acceleration for the free fall, which is 9.8 meters per second squared, but is not very far off. When you look at the velocity, you can also notice from the graph that the line is not very far from the line for the free fall, and the curve for the position is not very far from the curve for the free fall. Now, if we increase the value of k to 0.1 over second, and you can notice that here we have the values in the columns. You can notice that the values for the acceleration change a lot more. The acceleration has a tendency to go from minus 9.8 to minus 1.51, which is not far from 0. And we have that the time increases, fall time increases. The values for the velocity increase. So here we have the graph for the acceleration. You can notice that the acceleration has a greater tendency to reach the value of 0 meters per second square. The velocity doesn't increase in absolute value. The speed doesn't increase so much and tends to reach a specific value, a constant value. And the position, curve for position for k equal 1.11 over second is further apart than the red line for 0.01 from the curve for the free fall. So the parabolic motion tends to adopt a more linear behavior. And if we increase our value for k to 0.3, well, we can see from the acceleration curve that the acceleration for this line, which is for k equals 0.3, tends to 0 meters per second square. The velocity tends to reach some constant value, that is the terminal velocity, and you can notice that the line for the position tends to align. And of course, the fall time is much greater than that for the free fall, being more than twice the time for the free fall. The value would then correspond to more or less 33.945. Now we can approximate this better. It's too far off. Okay. Okay, here we have a better approximation. Here we are at less than, this is less than 0.1 millimeters from the ground. This is, I'm going to say that. Okay, so here we have seen the cases for which we can observe how the variation of values for K will produce the respective variations for the motion of the particle. So, in that way we conclude problem 10, and in the next video we will go to problem 11.